All right, let's dive in. Today, we're talking about something that's all around you, but you probably never see it. It's called systems engineering, and it's basically the invisible blueprint for almost every piece of tech you use, from your phone to the entire power grid. So let's pull back the curtain.
So to get us started, here's a little riddle for you. Think about an intruder alarm, a huge jumbo jet, and yeah, even that simple coffee maker sitting on your kitchen counter. What in the world could those three things possibly have in common?
The answer? They're all systems. And trust me, understanding what that one little word really means is the key to making sense of our crazy, interconnected modern world.
Okay, so our first stop is getting a real handle on what a system is, because it's a whole lot more than just a pile of parts.
Now, the official definition can sound a bit academic, but stick with me. It's a purposeful collection of interrelated components working together towards some common objective. The two words to grab onto there are interrelated and common objective. The parts aren't just sitting there next to each other, they're hooked together, they depend on each other, all to get one specific job done.
But here's where it gets really cool. When you put all those pieces together and they start talking to each other, something new is born. You get these properties, these characteristics, that you literally couldn't find in any single part by itself. It's this kind of magic that just emerges from all those connections.
To make this less abstract, let's actually take a system apart that we all pretty much get. We're going to do a little dissection in anatomy of a home security alarm.
Okay, so here are the usual suspects, right? You've got your movement and door sensors, you've got the siren to make a racket, a telephone dialer to call for help, maybe a voice synthesizer to talk to you, and the most important part, the brain of the whole operation, the alarm controller.
But see, these parts aren't just a jumble. We can actually group them by what they do. The door sensor, for instance, that's a sensor. Its whole job is just to collect information. The siren, that's what we call an actuator. Its job is to actually do something to the environment. Make a ton of noise. Then you've got communication with the phone caller, and the controller is the coordination hub, the conductor of the orchestra, making sure everyone plays in time. Every single piece has a very specific role.
And that brings us to, honestly, the most fascinating part of this whole thing. It's what I like to call the ghost in the machine. This is where we talk about those magical properties we hinted at a minute ago.
The proper name for them is emergent properties. And what that means is these are characteristics of the entire system that you can only see once everything is hooked up and running. They don't live in any one component. They literally emerge from the relationships between them.
This slide just nails the difference perfectly. Think about the total weight of our alarm system. That's easy, right? You could just weigh each part, add them all up, and you're done. But what about its reliability? How often will it fail? Well, you can't just add up the reliability of the sensor and the siren. The system's reliability depends on how they interact, the software, timing issues, a million complex things. That is an emergent property.
And here's the really crucial bit. This is also where things go horribly wrong. System failures, they usually don't happen because one part just breaks. They happen because of some weird, unexpected interaction between two parts that were working perfectly fine on their own. It's the ghost in the machine causing problems.
So if these systems are so complicated and have these tricky emergent properties, how do we even build them without everything just, falling apart? Well, that brings us to the process. You see, it's not random. There's a structured life cycle, a roadmap. It starts with defining the requirements. What does this thing actually need to do? Then you design it, break it down into smaller pieces. After you develop those individual pieces, you get to the really hard part, integration, which is putting it all together. And then finally, you've got installation, operation, and keeping it updated through its evolution until it's eventually retired.
And believe me, every single one of those steps has its own traps. Just trying to define something like reliability is tough. But the real moment of truth, the place where things often go sideways, is during that integration step. That's when you plug the hardware and software together for the first time and discover all the little problems you never saw coming.
Okay, so we've gone pretty deep into this stuff. But so what? Why is this so incredibly important to understand right now, today?
Well, here's why. It's estimated that in over 90% of today's complex systems, the thing that drives the complexity, the power, and the problems is software. We're not building as much specialized hardware anymore. We're using general hardware that's controlled by unbelievably complex software. And that means all these challenges of systems engineering, they're becoming more critical than ever.
So, let's wrap this up. What are the big ideas you should walk away with? First, A system is so much more than its parts because of those emergent properties. Second, the real danger, the place where things break, is often at the interfaces between components. Third, to manage all this, you need a disciplined, structured process. And finally, learning how to use systems thinking is becoming an absolutely vital skill for just about everyone in our software-driven world.
And that leaves us with one last, pretty heavy question to think about. Our world is basically becoming one giant system of systems. Everything's interconnected, it's all complex, and it's all driven by software. But as we build it, are we really truly prepared for the surprising, unpredictable, and maybe even dangerous behaviors that we're unleashing? Thanks for joining me for this explainer.